Good morning. My name is Bouselmi. I'm a regional extension agent working with the Alabama Cooperative Extension System. My program focuses on irrigation scheduling and improving water use efficiency. Today in my presentation, I will talk about irrigation scheduling for cotton, corn, peanuts, and soybeans. So deciding when to irrigate to optimize production is a daily judgment decision requiring consideration of several factors. One of the important factors is atmosphere, water, plant, and to take the right decision, uh, we should to understand the interactions between those factors. Can start by soil. An important function of soil is to store and supply nutrients and water to plants. Different kind of soil have different abilities to hold water, and plant can use an amount of water of this water holding in the soil, and we call it available water capacity. The available water capacity is the water held between the field capacity and the permanent wilting point. As you can see here, we have different available water for different soil texture. For example, available water in clay loam soil is more than available water for sandy loam. And to have this information help you to manage your irrigation for your crops and to have an idea about how much water your soil can hold. This table presents available water capacity by soil texture. For example, for fine sand soil, the available water capacity will be ranged between 0.75 to 1 inches per foot of depth. For sandy loam soil, it's ranged between 1.25 to 1.4 inches per foot of depth. As you can see, there is difference between different soil texture. Another thing we should to know about is the crop water requirements, to know how to schedule our irrigation and how much water our plant needs. The crop water requirements refer to the actual water needs for evapotranspiration, which are related to plant growth and primarily depend on crop development and climatic factors, which are closely related to climatic demands. For example, if we have high temperature and we have big leaves, so we have high evapotranspiration. So the climate have an impact to increase or to reduce the evapotranspiration. Also, the growth stage also have an impact on the water requirement of the crops. For soybeans use very little water during the seedling stage, and it increase during the productive stage. So any stress during the productive stage for soybeans have an impact on yield, especially during pod development, R3 to R4, and seed field R5 to R6. So to have an idea, for soybean is use very little water during the seedling, and increase will be sensitive to water stress during productive stage. Seasonal water requirements for soybean range from 15 to over 25 inches, and this is depending on planting date, maturity group location, and weather. And deciding when to end irrigation when beans have completely filled the pod cavity. R6 has been reached. This is when we decide to end irrigation for soybeans. For corn, require the most water just prior to and during the reproductive growth stage. During the vegetative stage, we have corn use less water compared to productive stage, but it's still more sensitive to water stress. Water stress in the tasseling stage leads to grain yield reduction up to 50%. And water stress during the productive stage, especially to can lead to grain yield reduction up to 80%. You can see how much is sensitive corn to water stress, and we should be careful when we manage irrigation for corn, because any stress have an impact on yield. So during settling and during hot weather, daily the transpiration or the water requirement for corn can be between 0.28 and 0.3 inches per day. So another thing we should take care about is when to end the irrigation for corn. Deciding when to end irrigation, we can breaking a corn cob in half allows us to observe the progress of kernel maturity. So as you can see in the picture, we bring the corn cob in half, and we can see the orange limit. This orange limit present the milk line, and this one give us an idea when to stop irrigation. You can see this table present the proportion of the length of bright orange grain and the relation between it and between the grain moisture for the grain. For example, if the proportion of the length of bright orange grain between 0 to 5%, so the grain moisture is below 60 to 58%. If the proportion of the orange line it's 20 to 25%, that means the grain moisture is below 50 and 48%. For clay soil, we stop irrigation when the proportion is between 30 and 40%. That means the grain moisture it's below 45 and 43%. For sandy soil, because sandy soil can hold a lot of water compared to clay soil, so it will be between 50 and 60% when we stop the irrigation. Peanuts. Now we move to peanuts. Peanuts have a very low water requirement during the vegetative stage, but water demand progress throughout the season, particularly during fruiting. The peak evapotranspiration rate is about 0.3 inches per day. So as you can see, for the first weeks, the water demand is low till the weeks number 5, and increase from 0.5 to 1.5 inches per week. And after 10 weeks from planting, the water use increase, and this is critical stage for peanuts, and we should be careful about any stress during this stage. Cotton need a pre-irrigation. Pre-irrigation is recommended to have a good germination. So during the emergence to first square, water demand is low. From first square to first flower, several water stress during this time can damage the cotton crop. The peak and the high water demand for cotton is from first flower to peak bloom, and also, like we said, any stress during this during this stage can have an impact on yield. From peak bloom to open bulbs, water deficit stress start to decrease and is less critical during this stage compared to the high stage. So to take the right decision and to uh, to schedule our irrigation with the best decision, we should use some tools, and those tools we call soil moisture sensors. And we have two types of soil moisture sensors. We have tensiometric sensors and capacitance sensors. For give you an example of one of tensiometric sensors, which it's watermark. It represents soil moisture status in units of soil water tension and registering the measurement in centibars. So, for example, if we have a measurement between 0 to 10 centibars, that means our soil is saturated. If from 20 to 30 centibars, we start irrigation in sandy soil. From 30 to 40 centibars, start irrigation in sandy loam soil. More than 40 centibars, start irrigation in clay soil, and more than 100 centibars, that means our soil is so dry. So those measurements help us to know the soil status and to know when to start irrigation. It's simple and to use, and we will see the advantage and disadvantage of this tool. The other type of sensor is capacitance sensors. Capacitance probes have the ability to measure the soil water levels at different depths down the soil profile and record information on data logger. So those this is a graph present the measurement with the capacitance sensor, and you can see those sensors provide more information and give you an idea about the volume of water on your soil, and you can monitoring your moistures or the moisture in the soil, and to have an idea about your field capacity and wilting point. As you can see here, this graph shows us the series of rainfall events. We can see the saturation after rainfall events, and also we can see our limit when we start irrigation. So the advantage and disadvantage of those two kinds of sensors. For advantage of capacitance, sensors can be used in high salinity environments, respond quickly, and have more accurate measurement. For tensiometric tools, the advantage is simple and it's not expensive. The disadvantage of capacitance probe, you need calibration, high cost compared to tensiometric sensor. Disadvantage of tensiometric sensor can't be used in high salinity environment and is not accurate in sandy soil. So those advantage and disadvantage give you an idea about those two methods or the two sensors. And as you can see, for sandy soil, tensiometric, they are not accurate compared to capacitance sensor. So we move to the result of our experimentation. Last year we had tested peanuts under rain-fed or dry-land condition and compared to irrigated condition. And as you can see on the left, the picture on the left presents the dry land, and picture on the right present the irrigated peanuts. And this experiment was in Dothan, in Landmark Park. And here the soil moisture balance in the root zone for the dry land. And as you can see, the rain provides just 57% of the water demand of peanuts. And we can see on the red circle present that the moisture is going down to the permanent wilting point. So we had stress after 90 days from planting. In this graph, we can see that the soil moisture, we provide irrigation during the dry period, and we provide 84% of the water demand for peanuts. So the result of yield we have, the irrigated is close to 6,000 pounds per acre, and the dry land it was close to 4,000. So we have difference about 2,000 pounds per acre, and we make our calculation, and after accounting for the pro-estate irrigation establishment cost and the cost of pumping the water, the net gain, it will be $290 per acre compared to dry land last year. This year we had some dry period, and you can see here the grass in headland in our experimentation station, and you can see the difference between the irrigated and the dry land for the grass. Other one, we have here the test between core dry land and core irrigated, and also this is in Dothan, and also we see difference between the irrigated and the dry land, and how much the water the irrigation can improve, also can keep your plant in healthy and growing as you want. And this is with a good scheduling and using tools that give you an idea about the right decision. And thank you for your kind attention. And if you have any question, just send me email or call me on my phone number, and I'm available anytime. And thank you.